Hi, welcome back to AP Physics C, Unit 9. This unit again is on electric potential. So we're going to, in this video in topic 9.2, we're going to talk about kind of what this unit is focusing on. All right, so the first thing, there is a difference between electric potential energy and electric potential. The difference is that electric potential describes the electric potential energy per unit of charge at a point in space. We'll get that equation written down here in a minute, but that is the definition. So as you can see, it's electric potential energy per unit of charge. So expressions for the electric potential energy for those different charge distributions that we talked about in Unit 8, we're going to have to use integration as well as principal, right? So principal superposition. So we're going to say V equals 1 over 4 pi epsilon naught, which again is K, the integral of dq over r. Okay, now for a point charge, V, right, this electric potential is kq over r. And if I have multiple point charges, I just simply add it up. So V would be equal to K times the sum of Qi over Ri. Right, so I just add up all these different point charges, right? Now, so the electric potential difference between 2 points is the change in the electric potential energy per unit charge when a test charge is moved between the 2 points. So delta V is going to equal delta U sub E over Q. Okay. Now, if we look at these graphs again, so these are conductors versus insulators. So the one on the left is a conductor, right, because E equals 0. And the one on the right is an insulator because E does not equal 0. Okay. Now, the reason why they look like this when you go from electric field to potential is because there is an equation that relates, or there's the derivative, okay, of V is the electric field. So the value for the electric field component in any direction is the negative of the rate of change in electric potential at that location. So remember, dV or ddx is a rate of change. Now, kind of on the flip side of it, if you're looking for the change in electric potential, what you're going to have to do is you're going to have to use an integral. So it's like you kind of, solving this equation for V. And so we say delta V, and then delta V is VB minus VA. So the potential at B minus potential at A. And it's going to be negative integral of E dot dr, right? So it's going to be a dot product. Again, it could be ER cosine theta. But this is why you see in these graphs here why the velocity, or excuse me, not velocity, the electric potential is a horizontal line until you get to the surface, right? So inside the conductor, the electric potential is going to be constant, right? Because if I take the integral of 0, I get a constant. And then when you go into the insulator, what happens is because an insulator in a V, the electric field in an insulator is constant, when you take the integral, you get this linear function to it, okay? And so then, but once you get to the outside, they become point charges, especially if they're spheres. Then it just gets this, inverse relationship, okay? Now, down in the bottom right-hand corner, what you're going to see is you're going to see what are called equipotential lines. And they are just lines of equal potential energy. So at each circle, like around that point charge, each circle represents a potential, an electric potential. And the electric potential difference is if I took 1 point and I went from this V, right, we'll call it VA, down to this V, we'll call it VB. Now I've created a potential difference, which means I have to do work against doing that. And the way you draw equipotential lines is that they're always perpendicular to the electric field vectors. The electric field vectors point in the direction of decreasing potential, right? So if I have potential down here and I have potential here, right? Basically, VI will be greater than, not less than, greater than, will be greater than VF, right? Because the lines, the electric field always points to decreasing potential energy. And then what happens is no component of the electric field along the electrical potential line, right? So there's no E kind of going, in this direction or that direction, okay? They only point radially outward, intersecting the equipotential lines perpendicular. And then the picture to the right is what happens when it looks like when you have multiple charges. So everywhere again. So the way you can think about it is equipotential lines are like topographical maps, right? That show the heights and how steep things are over time, right? And so they kind of represent the same thing. All right, so let's look at an example problem looking at electric potential. So here we go again. This is a derive an expression question. So this is derive an expression for the absolute value of the potential difference between the outer surface of the sphere and the inner surface of the shell. Express your answer in terms of Q, R, and physical constants as appropriate. So what happens is this is actually an AP problem. And previously, you would have discovered, or you would have found the E field, right, in that same region is negative Q over 4 pi epsilon naught R squared. And so this is what you're going to integrate. So we're going to say delta V equals negative integral of E dot dr. And we're going to evaluate that from R to 4R. That's the region, right, in the space. And we just kind of like whittle it down, right? And so I'm going to substitute in what E is. So E is negative Q over 4 pi epsilon naught R squared dr. Okay. Negative, negative becomes a plus. Again, we evaluate that from R to 4R. But this is all constant, so I can pull that out. So I get Q over 4 pi epsilon naught is the integral of dr over R squared. I would recommend rewriting this to be R to the negative 2 dr. Okay, because then you can easily see that this is now a power rule problem. So you're going to do plus 1 over negative 2 plus 1, right? And so you have all that stuff. And again, we keep writing evaluation. So we're evaluating from our limits are R to 4R. And I say delta V is Q 4 pi epsilon naught. And our answer here would be negative 1 over R. Okay. And we're evaluating that from R to 4R. Now what I can do here also, if I want to make this a plus, I can just make that a 4R, make that an R. And so I'm doing 1 over R minus 1 over 4R because, so we say delta V equals Q over 4 pi epsilon naught, 1 over R minus 1 over 4R. And now we just simplify this. So this becomes 4 over 4R, right? And so I get delta V equals, well, that's 3. So I get Q over, it actually ends up being 3Q because I get 3/4. This ends up being 3/4 R. Sorry, 3/4 over R. You get 4 pi epsilon naught big R. Okay, so that is the electric potential in this gap, or the difference, right, in that gap in our picture with the spheres. So now the last thing in this unit is going to be talking about conservation of electric energy, a topic that you've seen before because it's basically just, again, conserving energy.